Great. Today's lecture is about reducing randomness with random walks. Okay, so, all right, so of course, over the course of the semester, we've done all sorts of randomized algorithms, yada, yada, yada. Once or twice, we actually talked about de-randomizing algorithms. We de-randomized some of those SAT algorithms early on. And last time, we talked about de-randomizing the connectivity algorithm. So the goal is to figure out connectivity in log n space. We already knew we could do random walks to solve this problem in log n space, but we wanted to de-randomize it. And that's when we did some, we introduced, actually quite a lot of interesting ideas last class. A big object last class was the idea of an expander graph. So these are graphs that, especially constant degree expanders, so they're low degree graphs that are relatively sparse. You would think maybe they're simple in some sense, but they have constant spectral gap, where the spectral gap is the difference between one and the absolute value of any other eigenvalue. So if that difference is a constant, that means that you'll converge to a stationary distribution really, really fast, like exponentially fast. Okay, so an expander is a graph that on one hand is sparse. It doesn't have that many connections. On the other hand, it'll mix really fast as if it were really well connected, right? Like thoroughly connected everywhere. So it's sort of getting some kind of best of both worlds phenomena. The existence of expanders turns out to be really important in a lot of ways. We'll see some more connections today. So interesting properties, the diameter is always at most log n, just because a random walk can get anywhere in log n steps because you converge to a stationary distribution so fast. And you only need a constant number of random bits if you're doing a random walk on a low degree graph, right? I'm going to choose one of 10 neighbors or something. So if I wanted to solve the connectivity problem on an expander, then we could just enumerate all the paths of length log n, and that solves that. And to do general graphs, to solve the connectivity problem on general graphs, we had this like a crazy approach, which was to take your input graph G and try to transform it into a constant degree expander implicitly, because you only have log n space, so you can't actually rewrite the whole graph. And we did that with a sequence of graph transformations, this graph powering and this zigzag product. And roughly, we basically turned G into a constant degree expander, and then we can just enumerate all the walks of length n to solve connectivity. So what were those graph transformations? One is powering, right? So just taking a graph, and G squared would be, the graph, was one edge for every two edge walk in the original graph. Okay. And so really one step in G squared is like two steps in the original graph. So you'll converge to a stationary distribution twice as fast. Okay. So in general, the spectral gap gets much better. But remember, we wanted a constant degree expander, and the problem was that the degree goes up, right? Because now it's all the, 2-step walks, 3-step walks, 4-step walks. So the degree goes up. So we had to balance that out with something that can reduce the degree. And that's when we had this crazy zigzag product thing. The idea was we have some kind of regular graph G, and I want to reduce the degree. Okay. And we took a constant degree expander over D vertices. So let's say it's 100. So G has 100 degree 100. And we get a graph that has 100 vertices, and this regular was even smaller degree, say 5 or something. Okay. And it's a constant degree expander. And the idea was, in order to sort of simulate a one random step in G, okay, so that's like choosing one of 100, and you need log of 100 bits, okay? We also keep one vertex in H. So at any time, I have one vertex in G and one vertex in H, okay? But at some level, I'm really trying to do a random walk in G, but I'm going to use H to help me out. So I do a random step in H, which takes fewer bits because there's only like 5 neighbors, okay? And that's one of 100 vertices, one of D vertices, right? Let's say they're already numbered 1 through 100. So if this goes to like vertex 5 over here, I'm going to say, that tells me on the G side to go to the 5th neighbor of V. Okay, and that's the basic idea, is that I'm going to take one step in H, and I'm going to use that to choose a step in G. Okay, but you need less randomness to choose one step in H. Okay, and there's a few other steps added on, but that's actually roughly to make it so the whole thing comes out like an undirected graph, because what I just described is actually asymmetric. So you do a couple extra steps, okay? But the basic trade-off is at some level, instead of just choosing one of many neighbors in G, I only have to choose one of a few neighbors in H. Actually, I have to do it twice, but still, it's a win compared to, okay? So at some level, I now only need a constant number of bits to sort of do a kind of random step on the G side. And the intuition is that if H is a regular expander, then in general, it rapidly converges to the stationary distribution, which because it's regular is the uniform distribution. So if it's already at the equilibrium at the stationary distribution, one random step looks like a random choice of neighbor. Okay, now there's some quantitative difference because it isn't actually a complete graph. It's just something that's approximately a complete graph. And that's where we have to do some analysis, but that's fine. So it turns out that okay, you lose, the spectral gap goes down a little bit based on, something related to the spectral gap of H. But overall, if you combine, you take G, you square it, and then you take the zigzag product, initially the problem is that the degree went up. That's bad. But the zigzag product brings the degree back down. And then the spectral gap first improves from G squared, and then you lose a little bit from the zigzag product, but not too much because H was already an expander, so this is a constant, and you still overall win. So we were able to basically improve the spectral gap while keeping the degree the same in one step. Okay, something magical happened. All right, and then we only have to do that like logarithmically many times to eventually turn G into an expander. Okay, we also talked about some delicate things like making sure you can do this kind of implicitly. You're not going to reconstruct the whole graph, so you just kind of recursively query down based on the construction and stuff. But that was really more from last class. Okay, so we're going to build on those ideas in this class. So what we're going to talk about? Well, I guess I'll do a little bit of complexity theory at the beginning, talk about these classes, RP and BPP. But really the class is about doing more efficient amplification. I'll explain that in a moment. And we'll have to also make expanders again, actually even bigger than last time. Okay, so it should be doubly exponentially large. But anyway. Okay, so the general kind of framework, sort of a complexity style or framework, is we're going to be just looking at decision algorithms, so to speak. So, okay, how do we pose this? We say, oh, there's some language L, which is some subset of all bit strings, right? Graphs is an independent set of size K or something, just encoded as bit strings. And we're just looking at algorithms that take as input some X and decide whether or not X is part of the language. Just yes or no type algorithms today, as opposed to quantitative answers that we often have in other contexts. Okay. All right, basic classes. So you guys all know this. A language is in quote unquote P, stands for polynomial time, if there's a deterministic polynomial time algorithm to decide if an input is in the language. Okay, fine. The point is that we also have definitions for randomized algorithms. Okay, so here's the first one. So RP, which stands for randomized polynomial time, means that there's some randomized polynomial time algorithm that given X, if X is in the language, it should say X is in L with constant probability. Let's say 1/2. It doesn't really matter the constant. Okay. And on the other hand, if X is not in L, it should always say X is not in L. Okay, so it's one-sided error. It's allowed to have false negatives, I think, but not false positives. Okay, so that's RP. The one that allows for both sides of errors is called BPP. Okay, so if X is in L, it should say that X in L is probability at least 2/3. If X is not in L, then it should say X not in L is probability 2/3. Okay. Apparently BPP stands for bounded error probabilistic polynomial time. It's come up with like the biggest possible name for the simplest possible thing. Okay. All right. So how do I think of this? Okay. P means no error, no probabilistic error. RP is one-sided error. BPP is two-sided error. Okay. All right. So these subsets is pretty clear. Having no error It's better than having one-sided error, so P is a subset of RP. Having one-sided error is better than having two-sided error, so RP is a subset of BPP. Okay. Big question though is what's the difference? So we actually don't know if there's any separation between these classes. It's possible that P is equal to BPP. It's possible that P is not equal to BPP. I think in practice, if there's a randomized algorithm to do something, we kind of assume that someday we'll be able to come up with a deterministic algorithm, especially if, if we can do deterministic connectivity like last class, surely we can do anything is almost a hope. But nonetheless, we don't actually formally have an answer. We haven't actually proven that P is equal to BPP, okay? Or even if P is equal to RP or RP is equal to BPP. Okay, so this is a major question. Some people work on it. Sometimes this area is called pseudorandomness, which is really kind of a fine-grained understanding of how much randomization we need for various problems. Okay, so the topic today might kind of be filed under pseudorandomness. Of course, there's much more than we covered today. So as usual, I'm just exposing you guys to some of it. Okay, any questions? Okay, so let's talk about amplification. You guys already know this. All right, so let's say that I have some language in randomized polynomial times, which means I have one-sided error. Okay, so that means I have some algorithm that gives me, I guess, false negative error, where the probability of error is at most, say, 1/2. Okay, and let's say it uses m random bits for some fixed m on a fixed input size n. Okay, all right, how would I reduce the error probability to some given parameter delta? Okay, how many times should I run it? And what should I do? Okay, even if I run it again, now I have two answers or something, right? What do I do with those answers? How do I synthesize them? Average? Okay, so run it twice or x number of times where x is yet unspecified and average it. Okay. It's a false negative error, so don't average it. But if we see a positive, we know it is positive. Otherwise, we assume it's negative. Okay, so for one-sided error, sort of like heavy hitters, we can do the OR of all the answers. So if you get one yes, you know it's right away, because yeses are never wrong, but nos may be wrong. Okay, so it's slightly better to just take the OR of all of them. Okay, and the question now is, if I want to reduce it to delta, how many copies should I make? How many times should I run it? A log of 1 over delta, because then 1 over 2 to the log of 1 over delta, or whatever, should get you like delta. Okay, so, all right, so we've kind of done this many times, right? Run the algorithm log of 1 over delta time, take the OR of all the trials. Okay. All right, how many random bits do we use if we do this? All right, m log 1 over delta. All right, simple enough. The question is, can we do better? All right. You might think we couldn't because surely it's such a simple thing, right? Okay. Let's go through a similar exercise for BPP. Okay, so I have some algorithm that has error probability, say at most 1/3 for both the false positive and false negative, blah, blah, blah. And how would I reduce the error probability now to delta? Okay, run it multiple times and take the majority. Okay, so two follow-up questions. One is how many times? And the second is, how do I justify this works with good probability? Or with probability delta, I guess. Yeah. We could probably use the median trick. Okay, so I think there's going to be some connections and intuition with the median trick. Maybe we can, in hindsight, look at that. But one thing I'll suggest is that the median trick is often applied to more quantitative situations, like the thermometer question where I'm trying to figure out the value. Whereas here, this is a yes-no thing. In fact, what the median trick does is it takes a quantitative question and turns it into a yes/no, because you're hoping that each small group has an accurate thing, and an accurate one counts as a yes, and then the bad ones count as a no, and then you're counting up yeses versus nos, right? And you're hoping there's more yeses than nos, so to speak. Okay, so actually majority is kind of right and sort of syntactically right in terms of it being a qualitative thing at this stage, not a quantitative thing. Okay, but how do we justify that we should be right? Yeah. So how do I argue that the majority is right most of the time? Some sort of large. So let's say that you're given an input X and L, right? So your algorithm should be answering yes at least 66% of the time and no 1/3 of the time. Okay. So if you thought about that as like a number is 1 for yes, 0 for no, your average is 0.66. Okay. So if we run this like log of 1 over delta time, with high probability, you're going to be very close to 0.66, and in particular, well above 0.5. Okay, so the turn-off band will tell you that, okay, if it should be well above 0.5, then you're going to be above 0.5 with high probability. And you need about log 1 over delta. There, the epsilons, the usual epsilons from turn-off is just a constant now because, there's a constant difference between 0.66 and 0.5. Okay. All right, so same basic idea, slightly more sophisticated justification because we use turn-off instead of just this multiplying things together. Okay, but that's something we've done many times by now. Okay, same question as before. How many random bits do we need? Don't be shy. I know you.
Same.
Okay, same. And then again, the same question. Can we do better? Okay. All right. Well, there wouldn't be much of a lecture if we couldn't do better. I guess that would be one way to end the lecture early. That's it, guys. We're done. So I won't put it to a vote. Here then is the theorem. Okay. All right. So we can get, in fact, error probability delta, but instead of multiplying by log 1 over delta, I'm going to be using log 1 over delta additional bits. So before we had m log 1 over delta. Now we're going to go for m plus log of 1 over delta. Okay, so there's no multiplicative overhead. There's just an additive overhead. In fact, maybe m is bigger than log 1 over delta anyway, in which case it's almost no overhead. Okay, so it's pretty... these statements are just amazing, right? Because we have these very simple ways to do things, and sometimes things are so simple, surely they can't be improved. But this suggests they can. Okay, well, I gave you guys one small chance to try to think of some ideas. I don't know what you guys would come up with. But any ideas, even crazy, just for fun, just to get the juices flowing. How to do this? Yeah. Yeah.
But why are we choosing brand new M bits?
Okay.
Can we reuse some of the random bits from the previous?
Yeah, can we reuse some? Well, so certainly, especially when we knew a lot about the algorithm, we sometimes went into the middle and kind of dissected it that way. So I think, for example, of our randomized minimum cut algorithm, where we contracted a few edges and then we kind of press pause and we split off, right? So rather than completely restarting, okay, so maybe in some cases that's possible, but this is a relatively black box statement. All I know is that I have an RP or BPP kind of situation, right? I'm just assuming something as a black box. So, as far as kind of like what are the most important bits, what are the least important bits? What if the algorithm pretends to use m random bits, but basically ignores a lot of them or something, right? So that makes it harder to come up with a general thing, but it's obviously a good idea. Do we really need complete randomness? Certainly the bound is suggesting we shouldn't use m bits every time. Okay, yeah, maybe. Okay, can this use, okay, so we have m bits to start with that are already random, and can I use maybe a few more random bits to change some of the m change some of the m's, change some of it, which is pretty close to reusing most of it. I guess at some level, these two answers are both kind of true. I think what will be revealed is sort of, in hindsight, falls in like this. Um, any ideas for maybe a suggestion? So let's take that idea. I have m random bits, and maybe I want to use a constant number of random bits to somehow alter or update my existing m.
This theorem applies to every algorithm.
Yeah.
So then you might as well if we like shuffle the n random bits, change the order, but that would not work if the algorithm relies on like the parity of the n bits.
Oh, that's a good point. Yeah. Yeah.
So simple shuffling doesn't seem good enough.
Yeah. And in general, it seems like every time we get specific, we'll come up with some bad example because of this black box nature. Yeah. Ah, okay. So yeah, so even I don't know, maybe you have a few random bits, and I'll say, oh, I'll take these 10 random bits and replace 10 of the bits over here randomly, 10 randomly chosen bits. Except you're using more random bits to choose those 10 as well. That's 10 slots to replace. Oh, okay. If you choose the next bits by a random walk. Okay, so maybe you remember the title of the slide, the lecture. Okay, so the title of the lecture was reducing randomness with random walks. Does that help? This is like awfully hard to guess. I just thought it would be fun.
We encode the random bits as a graph, and then the path is the m path of length n is the random bits we end up using.
Oh wow. Okay. Good. Good. Okay. So here's what we'll do. All right. Okay. So we're going to make a really, really big expander graph, constant degree expander. Okay. We'll have to discuss how to make it at the end. But every vertex is going to correspond to one m-bit string. Okay. So there will be 2 to the m vertices in this graph. Okay. So that's why some of the vertices are annotated and the rest of the vertices I got tired. Okay. All right. But there's bit strings attached to those vertices. So, okay. All right, so we're going to make a big expander graph where every vertex is identified with one of these random bit strings that can be fed into the algorithm. All right, now what we'll do is we'll take a random walk in this graph. So I will choose, the first vertex uniformly at random, like here or something. Okay, so it takes m bits to choose one of them, right? Because there's 2 to the m vertices. Okay, so that's my m random bits initially. And then every time I take a random step, let's say I go here, how many bits do I need? Constant, because it's going to be a constant degree expander. Okay, so I'm going to do a random walk for roughly the same number of steps like we had before. Uh-oh. Right? Something like this. Okay. And what we'll do is every vertex I visit, that's going to be a different random input, kind of random bit string used for another trial of the algorithm. Okay, so your first trial will be the first sampled vertex, and then the second vertex on the walk will be for the second trial. It will be the random bit string used by the algorithm the second time, and then the third time, random bit string, and so forth. Okay, does that make some sense? Can we what? No, so oh yeah, so okay, so can we build the expander in Polyton? Good question. Luckily, I'm exactly prepared for this. All right. So this graph is going to be of size 2 to the m, right? So even to do something polynomial timing the size of the graph, I'm screwed because the graph is already exponentially sized. So it'll be at the end of the lecture, but we're going to have to do something similar to last time, where we do some like zigzag products and tensors and some crazy stuff, so that we can implicitly build the graph and be able to kind of simulate a random step, in that kind of oracle model, without ever actually building the graph explicitly. Yeah.
Do we need any randomness in building the graph? Because wouldn't we need more random bits to construct this graph?
So in fact, the answer will be no. Yeah, yeah. Because, well, the graph at some level, you're going to start with one small constant degree expander, which is already exists. Is mathematicians already invented one for us. And then we're just going to keep ramping it up like last time. We'll take powers and tensors and zigzags. And those are just these like graph combinatorial, transformations. There's no randomness in them.
So the concern I have is that wouldn't there always be a relationship between V1 and V2? Because V1 and
Yes.
V2 would be.
Yeah. So first of all, let's remember what's going on. At some level, we are claiming that I can replace log 1 over delta uniformly random samples with sort of a paths from a graph that's fixed, right? So V2 and V3 and V4 are always going to be paths in the graph. They're always going to be connected with an edge, and V1 was already going to limit where you can go by V10, right? V1 will be sampled uniformly at random, so you could start anywhere. That's okay. That's a help. But yes, absolutely. So but the starting statement's already surprising. The claim that I can replace m random samples with something that's not completely random. Not completely independent. Okay. Maybe we should talk about the intuition. Anyone want to try to explain the intuition for our approach? Maybe the previous slide would be better because it has at least a picture drawn. Intuitively, what are we trying to do here? Anyone want to guess? So I want to simulate log 1 over delta uniformly random samples. Why would this have any correlation with that?
Well, the first sample we know is in fact uniform.
Great. Then I do a random walk, right? How do random walks behave on expander graphs? Huh? No. Yeah. Well, it's not that they're sparse, it's that the spectral gap is big.
So you converge to the stationary distribution, which is the uniform distribution.
Yeah, so random walks converge to a uniform distribution over time. So there's some quantitative difference between a random walk and a completely random thing, but that's captured by this gamma, so we'll have to do some calculations moving this gamma around, but we can ultimately bring it kind of under control. Okay, so the intuition is that random walks and expanders behave like, which is quantitatively measured by the gamma, behave like uniformly randomly sampling the graph because they mix so fast. Okay, so yeah, the existence of, so we need two things at the same time. We need low degree, so we only need a constant number of bits each step, and we need rapid mixing, right? So that each step actually behaves almost like one of n instead of one of 5. So it's really, something's kind of phenomena. The phenomena of the existence of constant degree expanders is tremendous. It's really doing a lot of work for us. It's a very strong gadget. Okay. All right, so that's the intuition, and then we'll have to, labor through to get that down on paper. So okay, all right. So what are some other comments to be made? Um, okay, so we already said, right, you only need m random bits and a constant number of bits for each one. That's how you get the total number of random bits in that theorem. And then like we said, the intuition is that we hope this is going to behave like uniform sampling. If it was exactly uniform sampling, then we have the same thing as before and we're done. Okay, what's next? Okay, so let's step through what happens in the RP case, randomized polynomial time. So there we said, okay, we take the OR of a bunch of independent trials, right? So what would happen here? Okay, so let's say a vertex is bad if the algorithm makes error, has an error if it uses that vertex. Okay. And I'm letting capital B denote the set of all bad vertices out there. Okay, maybe you can imagine this shaded region in the middle is like all the bad vertices. Okay, although that looks like more than 1/2, but oh well, it's still a constant fraction. All right, okay, so if I did this random walk, for a while, and outputted the OR of all the trials on the vertices, then this is going to fail under what conditions in terms of B's and random walks and stuff like that in graph terminology? Yeah, if the whole random walk stays in B, that's the only way this approach can fail. Okay, good. All right, so it's going to fail if and only if the entire random walk is stuck in B. The random walk can escape B, then good, right? In fact, here we can even make a connection to conductance, right? Remember, conductance is this idea of having lots of edges leaving any particular set, right? So an expander graph is going to have large spectral gaps. So it's going to have very good conductance. So you're thinking that, oh, out of B, there's many edges leaving B, or a constant fraction of edges leaving B and stuff like that. So you're hoping that you can escape B fairly rapidly in an expander. Okay, so that is this is the theorem that we'll actually have to analytically prove. So in general, if you give me some regular undirected graph with a spectral gap of gamma, and I have some set of bad vertices, okay, I'm letting mu denote the fraction of bad vertices. And I want to bound, okay, what are the odds that my entire random walk is stuck in B? And this will be at most 1 minus 1 minus mu gamma to t. Okay, so let me interpret that. Let's say B is at most half the vertices, like RP, you have a constant error, like 1/2 error. So this will be gamma over 2 to the t. So if gamma is a constant, gamma 2 over 2 is a constant. So this is roughly exponentially fast in t. All right, so that's what we'll prove. Sorry. It's really a graph statement. Okay. All right. Okay, so for BPP, okay, this is where we take the majority vote. All right. And let's say, again, we have some bad vertices and it's most 1/3 of them or something. When we do the majority vote thing, we're going to fail if and only if at least half of the random walk is in B. Okay, so as long as we can escape it most of the time, we should be in good shape. Okay. And B represents much less than 1/2 of the graph, so you're hoping, on average, that should be the case. Now, if you remember, to justify our amplification for BPP, we ultimately appeal to Chernoff bound. So we have a much messier, but sort of Chernoff-looking statement. Let me explain. In fact, there's some typos here. Okay. All right, what is this statement? Okay, so let's say that G has a spectral gap 1 minus epsilon or something. Okay. Okay. So here's one way to sort of formulate it. Imagine for every vertex, I've assigned basically a value f of v. So in our context, f of v is like yes or no or 1, 0. But the statement could potentially be more broad and just be any value between 0 and 1. Okay. And at some level, okay, let's let mu be the expected value of a completely random vertex. So they average over all the vertices in the graph, right? So we're going to look at sort of like, okay, I take a random walk for 100 steps and I average all the values I saw. So I walk around and I keep getting f of v points, f of v points, f of v points. Okay. And I look at the average of what I got compared to the true average out there. Okay? The question is, okay, what happens when I deviate from the true average, epsilon mu plus beta? One thing here, be careful about is epsilon is actually tied to the spectral gap. Epsilon is not a parameter we get to choose. Okay, but still, at some level, what are the odds that this kind of random walk of collecting points on an expander deviates from the average? Okay, it's roughly kind of e to the epsilon k, epsilon minus beta. Okay, yeah, okay, and that'll be enough for our case as well. Okay, but I think what's important is that sort of syntactically, this sort of looks like a Chernoff style statement in terms of like a sum over the vertices of a random walk. Okay, and you do get concentration, although there are some kind of technical issues, like the fact that epsilon has to be tied to the spectral gap as opposed to we get to choose it. It's a little bit annoying, although often we can sort of improve the spectral gap by powering or doing something a couple extra times, and we still have some control over epsilon. Okay. In our application, we also have um, uh, we also have control over mu, right? Because let's say that my algorithm originally had, probability of success 2/3 or something. I can do a constant number of amplifications and get that up to 99 out of 100 if I wanted, before applying the theorem and stuff like that. So for this application, it'll be okay. Okay, great. And at the end, so those are the two lemmas we're going to prove. The third thing at the end is also how to build the graph. And that'll sort of build on some ideas from last class. Okay, so let's do this one first. I hope we have time for that more complicated Chernoff one, but if we don't, then we'll skip it. Okay, I mean, at some level, well, at least some ideas will come here, and maybe I can still walk through the high level steps of the Chernoff, and that'll be fine. Okay, all right, so let's prove the slightly easier one. What are the odds that the whole random walk stays inside this set B? Okay. All right. So G is a regular undirected graph with spectral gap gamma. B is our bad set. Mu is the proportion of the graph that the bad set represents, and I have some random walk. All right. Here we go. Okay, so R is going to be the random walk matrix on G as usual. Here's something new. I'm going to find P. P is going to be the projection onto the bad vertices. So if you give some X to P, okay, what it's going to do is it's going to keep the coordinates that stay in B and zero out everything else. So X of V, if V is in B, if V is not in B, I'm going to set it to 0. So P is just going to erase the coordinates outside of B. That's the projection onto the subspace R to the B. Okay. So if I look at PRP, what does that do to a random walk? So imagine I'm some distribution over the vertices, and I apply PRP. What does that do to it?
Like the matrix is now only for walks that start in B and end in B.
Yeah. So at some level, it's sort of restricting our attention to B. Okay, so first it goes P. So the first thing P will do is going to zero out all the coordinates outside B. So it's going to drop all the probability mass outside B, remove it from the system. And then what's left is whatever's inside B. Then we take a random step, right? So that's going to move some stuff in B, but it's also going to move some stuff out of B. And then the last P is going to annihilate whatever moved outside of P. Okay. So all put together, yeah, it's a 3-step thing, but it's really kind of throwing everything out of B twice. All right, so let's focus on the first blank. How would you interpret this expression? PRP to the T times 1 over n is this uniform distribution over all the vertices. So I'm starting with a uniform distribution over all the vertices, and then I'm applying PRP T times. And then at the end, I'm summing everything up when I apply that last all ones. Okay. So I start uniform over the graph. I do PRP, 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 and I'm left with some distribution over the vertices, and I just add them all up. Almost. So you're adding them all up. So at some level, there's sort of the probability that it could be on any vertex after t steps, because you're adding up all the probabilities at the end as opposed to a particular one. Except some things have been zeroed out and stuff like that. Actually, you're still in B because everything outside of B became 0. Okay, so that's actually close, but it's not quite. So that's very close. The probability that we're still in B at the end. Ah, okay. So as soon as you leave B in the middle, you also get killed off. So this is actually the probability that the whole random walk stays in B, including the first sample. Okay. All right. So this actually is some, big linear algebraic way to describe exactly what we're trying to analyze. All right. So, okay. So now I want to figure out the probability that the whole random walk stays in B. I've sort of turned this into a linear algebraic expression. I'm excited about that. You guys are less excited about that, but that's okay. um, okay, but why is it useful to pose it this way? Okay. All right. So first, let me rewrite this. N is 1 dot product 1. Okay. So this isn't doing too much. But at some level, you can also think of this as normalizing each of those outside ones. I'm missing something on my inner product. Okay. Right. So at some level, it's really ones divided by square root n on both sides. Okay. All right. So, but what does this expression sort of look like? So it sort of looks like an eigenvector computation, right? Because in general, if you're given a symmetric matrix A, the maximum of xax will give you over normalized x's will give you the top eigenvector. Okay. I think one thing maybe I didn't stress before is that actually P is symmetric because actually it's a diagonal matrix with only ones along B and 0 everywhere else, and R is symmetric because G is a regular graph. So if it's a regular graph, the adjacency matrix is symmetric. Okay, which is actually why last class that also applied last class, but I forgot to say it explicitly. Okay, so R is actually already a symmetric matrix for us, which is very convenient. It's actually equal to the normalized random walk matrix as well if you happen to work it out, but no big deal. Okay, so good. Okay, so PRP to the T is actually also a symmetric matrix. Okay, so really this is going to be bounded above by kind of the maximum absolute eigenvalue of PRP. Last class, we introduced the operator norm as a fancy way to express this. Okay, but it's the maximum absolute value of any eigenvalue of PRP. All right. Okay, so the nice thing then is that, I mean, concise or opaque as it may be, is certainly very short, which gives you some hope that it'll be analyzable, right, compared to the original Messier statements. All right. All right, so the claim now is that this maximum absolute eigenvalue is at most 1 minus 1 minus mu gamma. I plug that in here, raise it to the t, and then we'll get the original statement. Okay, so we just have to do some eigenvalue analysis, and then we're done. Okay. All right. So, okay, so let's prove this thing. So first of all, as I mentioned, G is the regular graph, so R is symmetric. Okay. So we can apply the spectral theorem directly to R. Okay. The first eigenvector of the random walk matrix is, yeah, all ones. So we even know the first vector that shows up in the spectral decomposition. All right, so we have something that looks like this. Mu2 through mu n should all be orthonormal, and orthonormal was the all ones vector. Okay. And then mu2 through mu n are all eigenvalues that are smaller. In fact, they're all, the absolute value is at most 1 minus gamma, because gamma is the spectral gap. Okay. So we can write this as, gamma over n times the ones matrix plus r prime, where r prime is something with spectral gap. Well, we was operator norm as most 1 minus gamma. Okay, so all I'm doing is ripping off a small chunk of the 1 by 1, the 1 outer product 1, a gamma over a gamma chunk, and then leaving the rest there and putting it into r prime. Okay, so if I plug that into PRP, did I write it? No. Okay, so what do we get? We get something like gamma over n, the outer product of, well, I'll do it slowly. P ones P plus P R prime P. Okay. All right, so one thing very convenient about the operator norm is that we have things like the triangle equality and stuff like that. So we can do this. Okay. In fact, we can do even better. We also have stuff like this. Okay. I can even break that up multiplicatively. But the point is I'm left looking at the operator norm of relatively small parts. Okay. Let's start with the easier ones. What is the maximum eigenvalue of P? So P is the kind of projection, or it's just saving the 1, right? Because it's a diagonal matrix with some 1s and 0s on it. Okay. All right, so that's at most 1. What's the operator norm of R prime? 1 minus gamma. Okay, this is at most 1. Okay, so now let's look at this. Okay, so P, 1's outer product 1's P. Well, this is actually the same as applying P to each one. Okay, in part because P is symmetric. Okay. All right, so it's really an outer product of just one vector with itself. This is really just a ones vector in B, just ones for vectors, vertices in B, and 0 everywhere else. So what would the maximum eigenvalue eigenvector look like for this? Just a rank 1 term, and just keep in mind this is the same as P1 transpose. So in general, it's the maximum eigenvector of something that looks like X outer product X, which is the same as X transpose. Okay, well, we know from the spectral stuff that some level I want to maximize over, say, all unit vectors y, something like that, right? But this is equal to y p1s squared, okay? So at some level, if I wanted to choose a direction y to maximize p1, so this is constrained to unit vectors y, how would I try to maximize this? So I have some vector, right? What direction do I choose so that if I project it onto that direction, I have the best length, same direction. So it should be something proportional to p1s. And the length you'll get is the norm of p1. Okay? So the maximum eigenvalue of a rank 1 term is just the norm of that. Okay, okay, so this is p1s squared, okay, for the appropriate choice of y. Now p1s is just making everything outside b 0, and everything inside b stays the same. So what does that actually come out to? Sorry? Uh, it'll come out to the number of vertices in B, because you're getting 1 point for every vertex in B. Okay. But if we plug that in back above, okay, so what do we have? We have gamma size of B over n plus 1 minus gamma, and mu was the number of was B over n. And this is what we wanted. Okay. All right, so takeaway is, yeah, random walk will leave a set in an expander. All right. As usual, everything is just governed by the eigenvalues of the random walk at the end of the day. All right. It seems, of course, exotic to deal with this because I think it's new for everyone. But if the mathematical aspects weren't new, then in hindsight, it's actually it's quite a transparent analysis into the heart of like what's going on. It's kind of hard to look at a graph and analyze a random walk directly, right? So to be able to do this systematically was relatively little work. Is very nice. Okay, so all right, I won't do this in detail then, but I do want to point out some high-level ideas. This is risky. Okay, let me at least explain the setup, and I won't do all the calculations. All right, so I want to prove this Chernoff style statement. Okay. All right, so okay. All right, so in general, I don't know, lambda will be whatever I want to be on the right-hand side later, right? But in general, I'm looking at a statement like this. So you want to guess what the first step might look like. We're gonna proceed just like the Chernoff bound and exponentiate both sides and apply Markov's inequality. Okay. All right, so you get something uh, like this for some parameter t, say between 0 and 1 to be determined. Actually, eventually you take t equals epsilon. Okay. Now, oops. Okay. Okay, here's maybe the one kind of really interesting part of the proof. So we introduce this matrix F, which on the diagonal has sort of these exponentiated Is that the diagonal from your point of view, or is it this way? Is that the diagonal? Is that the diagonal? No, no, if you do, it doesn't help me. Is this the diagonal?
Yes.
Okay. So it has e to the t fv1, fv2, fv3, fv4. Okay, all along the diagonal. Okay, so you put that there. Okay, this is the one I think kind of really subtle part of the analysis. All right. Now, okay. Okay, so what did we learn last time from the last proof? Is that if I can somehow take that relatively complicated statement I'm trying to prove and turn it into some statement that looks like this, then afterwards I just, analyze some eigenvalues of this, and while new, it's still relatively kind of straightforward in some ways. You just have to chug through some math. But the hard part is sort of getting there, in my opinion, and reducing it to a more straightforward eigenvalue computation. Okay, so the claim is that this crazy statement, the expected value of e to the fv1 plus fvn, it shouldn't be fvn, it should be fvk, right? Because these aren't the vertices in the graph. These are the vertices of the random walk, right? So keep that in mind. So the expectation is over random walks in the graph v1 through vk, and we're looking at exponentiating all the values you see along the way, right? Which is just blowing everything up, right? It's just putting everything on steroids. Okay, so it's claiming that the exponential of your random walk values is some very compact expression. Okay, all right. So how do we interpret this? Well, how do you interpret that? Um, how would I even interpret, something like just the part underlined, RF, right? What if what is, RFP, where P is some distribution over the vertices? Okay, so I'm at some distribution P, maybe I'm at a fixed vertex, and F is going to sort of like collect e to the t of fv1 points for wherever vertex I'm on, right? Because F is just going to, is the diagonal, and so whatever vertex you're on, you sort of collect that many points. Think of them as like coins, like Mario. So it goes like ka-ching, and then you get some points. Okay, and then you take another random step with R. Okay, and that'll send you into a new distribution along the thing, and then you go ka-ching, you get some more points, right? So then you take a random step, and then you do F again, and then it goes ka-ching, you get some more points, except it's multiplying together as opposed to adding. Okay, and then you do another R, you take a random step, and you get another F, and that's another ka-ching. Okay, all right, so okay, so something like FR times, say some uniform distribution over the vertices is like first taking a random step and then collecting points based on the vertex you're on after that random step. And to do that over and over again, it's like repeatedly taking the step, and each time I collect e to the fv along the way. Okay, although they kind of multiply together as opposed to adding when I say collect. Okay, so that's actually how you interpret this: is that you start really you have ones over n. So you start the uniform distribution, and you're taking a random walk for k steps, and you're collecting vertices along the way, collecting points at the vertices along the way. Okay, so that's sort of how you actually get this expression. And then at the end, you add it up, and that's just summing over everything. All right, so that's how these things map. Of course, you could spend a little more time to draw this out explicitly, but that, I think, hopefully this makes sense. Okay, so once you have that, then you start doing something very similar to last time. I'm going to take R, I'm going to rip out, one piece for the first eigenvector, and then one piece for everything with maximum eigenvalue at most 1 minus gamma, and start analyzing things like this and stuff like that. Things are a little bit messier than last time because of all this e to the t stuff compared to before. Okay, but the high level ideas are kind of similar, but we keep kind of doing some operator norm bounds. Okay. So I'm skipping the calculations, yada, yada, yada. And you just keep kind of chugging through. Okay. And eventually you're ultimately able to bound this thing using those tools you built above. And then you choose the best T in hindsight, kind of like you do with Chernoff. Okay. So I think the main step is to figure out how to introduce this F to turn it into an eigenvalue computation. Okay, and then from there, it's a little bit more like messier than last time because the exponential, and then at some point we do the whole e to the x is less than equal to 1 plus x squared inequality, just like you do with Chernoff. So imagine just taking that last proof and taking the Chernoff proof and those kind of tricks that show up in the standard Chernoff, and then they have a child. Okay, and that child is the part I'm skipping. Okay, all right. Okay, good. No complaints, I think. All right. Okay, so that is the rapid proof of this. Okay, but I think at least we got the main conceptual ideas. Let's do this because this part's fun too because it was graphs. Okay, so last but not least, how do I make a graph like this that's so big? Okay. Now, one thing compared to last time, I don't have to be as uptight about memory, about space usage. Last time it was log space. This time I don't have to worry about that, but I do have to be mindful of, in general, being efficient and stuff like that. Okay. All right. Okay, so here is the construction we're going to do. We're going to start with a constant degree expander with some degree d and d to the 8 vertices and like a very large spectral gap like 7/8. Okay, we're just going to assume they exist. In some homework problem, I think we'll ask you to make one. Okay, but they'll give you some steps. Actually, I think this one's going to be a toughie, if I remember correctly. It'll be a tough one, but that's okay. All right, so G1 is just going to be h squared. Now, in general, given G10, how do I make G11? I'm going to take, I haven't defined this yet, but I'm first going to take the tensor product of G10 with itself, and we'll define what that means momentarily. It's sort of like a product graph. It's pretty intuitive. Then I'm going to power it. So whatever is that tensor graph, I'm going to take all the two-step walks, look at that graph, and then I'll do a zigzag with H again. All right. So just to remind us, or for those who missed last time, okay, so powering, I already talked a little bit earlier, but it's just a graph where I'm taking each edge corresponds to a k edge walk in the original graph. So that increases the number of edges by a lot, increases the edges by the degree by a power of k. But the good thing is it improves the spectral gap a lot because one step in this powered graph is like k steps in the original graph. Okay, so you're kind of speeding things up. Okay, so that's usually where we start, and then the whole rest, a big part of the rest of the game is, okay, how do I bring the degree back down? At least that was the case for connectivity. The zigzag product, again, the high level idea is I have some graph G with pretty high degree, and I want to reduce the degree, right? And so we kind of introduce a smaller graph H, okay, where the number of vertices in H matches the degree in G, so that instead of taking a completely random step in G, I'll take a smaller random step in H and look at the index of that vertex to simulate a random step in G. I never actually do any randomization in G. Okay. There's a couple other steps to make it symmetric. So so first I step in G, then I move in G to the neighbor, and then in reverse, in H, I go. Okay, so if I go from here to here, and if I look backwards, and this was like the 10th neighbor of this, then this is going to go to vertex number 10. And then I do one more random step in H. The last two steps, actually, all it does is make the whole process symmetric. Okay, because if we didn't have a symmetric graph, then analytically, like, everything goes to crap. Okay. Okay, so the main things was that in the zigzag product, the degree is going to be something like the degree of H squared, because you do two steps in H. And the spectral gap goes down something based on the spectral gap of H. In particular, if H was a constant, had constant spectral gap, it'll go down by a constant. Okay. All right. Okay, so what's left to define is the so-called graph tensor product. So this definition actually makes some sense. Let me first explain remind us a little bit about tensor products from last time. In general, if you have two linear maps, then A tensor B is the linear map that sort of takes as input a matrix C and outputs A, C, B. Okay, so that's a linear function over the space of linear functions. Okay. You know, some identities to help you out, A, B, C, D is A, C, B, D. Okay. But an important fact that roughly follows from this, let's say A and B are symmetric, A tensor B will have eigenvalues of the form lambda A, lambda B, where lambda A is an eigenvalue of A and lambda B is an eigenvalue of B. Okay, in particular, if the eigenvector was like X and Y, X outer product Y will be the corresponding eigenvector for AB, and that roughly follows from this. Okay, fine. Who cares? Okay. All right, so what do I mean by graph tensor? So this sort of makes sense. Let's say I have two graphs, okay? And the idea is I first kind of look at sort of the product graph. So any point in time, I have one vertex in graph one and one vertex in graph two. And steps are kind of done simultaneously. So an edge looks like an edge here and an edge here. So a random step will move both at the same time. Both at the same time. Okay? So that's sort of like a product graph. One important fact, if R1 describes a random walk for G1, R2 describes a random walk for R2, then the tensor as a linear map, R1 tensor R2, R1 outer product R2, actually will give you the random walk for G1 outer product G2, which you can verify using some of those algebraic identities on the previous slide. Okay, so it gets a little tough to think about because suddenly like the number of the dimensions are kind of going crazy if you thought about it that way. But if you just verify the identities and you just kind of say, okay, it seems okay, and then life goes on. Okay. All right. Because it always gives me a tough time too. Okay, so all right, a lot of new stuff for a lot of us, but here's basically all the facts we need on the right. Okay, so what we're just going to do is say, okay, when I start at G and I do one of these steps, how does everything develop? Okay, all right, so first so G has n vertices, degree D squared, partly because we did the zigzag product was H in the previous iteration, which will leave you with a graph of degree D squared. Okay, and spectral gap gamma. Okay, all right, so what does G tensor G, how many vertices are in that graph? N squared. What is the degree? D squared. Why D squared? Yeah, so you're taking steps simultaneously, right? But you get to choose one edge from here and one edge from here. So you get D squared choices here and D squared choices here. So you multiply them, you get D to the fourth. It's actually D to the fourth. What do the eigenvalues look like? In particular, what's the spectral gap? So here you want to use this fact. A tensor B has eigenvalues lambda A, lambda B. So you're probably thinking like, oh, let's say that mu2 determines the spectral gap, right? Like gamma is 1 minus mu2. Then you're probably thinking like mu2 squared would be a new spectral gap. But slight catch. So it's any eigenvalue of the form lambda A, lambda B. So actually you have eigenvalue 1 from one map and then mu2 from the other. It's actually the same. The spectral gap actually doesn't change. Okay. All right. Okay. Now I take this graph and I square it. So I'm looking at all the two-step walks become the edges. All right. How many vertices? Does not change. What is the degree? Huh? Okay. So we'll square it and that gives us d to the 8. d8. Like chess. Okay. And then what do the spectral gap look like? Huh? Yeah, we're just squaring. Oh, so it's slightly. So if you look up here, I don't know if you can see. So it's actually 1 minus gamma squared. Because yeah, mu2 would become mu2 squared, but mu2 is 1 minus gamma. So you have to do it a little bit more clumsily. All right, so 1 minus gamma squared, which is something like 2 gamma minus gamma squared. So we get to roughly double the spectral gap. Okay. And then, okay, now I take the zigzag product with H. Okay, so H has degree D and D to the 8 vertices. That's odd. Oh no, that's okay. Okay, sorry. Okay. I got worried about something. Okay, so note that the number of vertices in H matches the degree in this graph. That's important. That's what I got hung up on. Okay, so the zigzag product. Okay, so first the vertices was the product of one and the other. Okay, so how many total vertices are there? N squared d to the 8. There seems to be a typo in the notes saying n squared d to the 4th, but I'll fix that later. Doesn't matter too much. Okay, what is the degree? D squared. And what is the spectral gap? Oh, sorry. Okay, so it should be 2 gamma minus gamma squared times 7/8 or something squared. Okay. Now, I seem to have convinced myself, I didn't actually double check, that if gamma is at least 1/2 to begin with, then 2 gamma minus gamma squared times 7/8 squared would allegedly be bigger than 1/2 again. 3/4 times 7/8 squared. I don't know if anyone wants to do that quickly. Okay. Otherwise, I'll, change the numbers as convenient. Is that correct? Okay, good. That's all I really need is your confidence. But the point is I keep the spectral gap high, except I've taken a number of vertices and I've squared it. I didn't even double the vertices. So I maintained the spectral gap. Actually, H originally had good spectral gap. So I'm not trying to improve the spectral gap. I'm trying to ramp up the number of vertices really fast. And here I was actually taking n vertices and outputted n squared. Okay, so the number of vertices goes way up each time. So to go from constant to 2 to the m, which is how many we need, how many times do I have to square? The log of m? Yeah, so it's really log of 2 to the m. So if you're squaring, then if you get log on the other side, it's opposed to a log. So log of 2 to the m will give you log of m. So you only need to do this log m times. So okay, there's a little bit of log m overhead to build this thing out, but that's it. Okay. So rather than build this explicitly, sort of if you need to take one step, you sort of reverse engineer what's going on in the previous graphs, and you just kind of keep going down and recursing. So you never actually build it out. You just say, oh, in my theoretical G100, I want to take one step. I want to go to the 10th neighbor. I reverse engineer based on the zigzag product. Oh, that's the 9th neighbor of the previous graph, 8th neighbor of the graph before that, and so on and so forth, and recurse all the way down. And then you never actually have to build out the whole graph explicitly. Okay. All right, so that puts everything together. If you check all the numbers, you'll get the theorem at the end, and that's the idea. All right, thanks, guys.